Right, notebook 7a, Ridge Regression on Amy's house pricing. Packages, directories, functions. Now, what do we have here? IDX train. Train is 60% of the data, foals 0 through to 5 inclusive. Validation is 20% of our data, and test is another 20% of our data. We are going to fit lots of models on the train data, and for each of those models, we're going to see how well it does on the validation data. When I say we're going to fit lots of models, I mean because we're going to try lots of different values for lambda. We will look at the performance of the models on the validation data and see which lambda performs best on the validation data. Once we've done that, we will fix that lambda and then create one final model on the train and validation data together, which we will test on the test data. I hope that made sense, but we're going to do it now. Let's go. Well, would you believe it? I just did what I promised myself I would never do, which is to record that whole session, except the recorder was on pause. So I'm going to have to do it all over again. Here we go. It might be a little bit on the quick side this time. I hope you can follow. We're going to fit 20 models for different values of lambda. For each value of lambda, we're going to calculate how well that model performs on train and on validation. We don't really care how well it performs on train. It's obviously going to get better and better and better as the model gets more complicated, because anybody can overfit a model on the training data. The question is really how well does it perform on the validation data. We're hopefully going to find that as the complexity increases, the validation performance first improves, the loss function becomes less, but as the data becomes more complicated and the model is just really fitting itself to noise in the training data, which is different in the validation data, the validation performance will actually get worse. If we can find that sweet spot, the balance between bias and complexity, then we will fit one final model with that value of lambda on both the train and the validation data together, and we will test it on the test data. How are we going to create these lambdas? Well, a list comprehension is one way, 2 to the power of num for num in range 20. How are we going to create a data frame? Well, I'm sure there's loads of ways. We'll just use a dictionary. We're going to need keys for lambda, for MAE train, and val, and for RMSE train, and RMSE val. And the values for most of these keys are just going to be some kind of placeholder. We'll use the NP, not a number, as our placeholder, but we know what the lambdas are because we just created them. Oh, that didn't work. Great. What went wrong there? Not quite sure what I thought I was doing. That looks better. Let's have a look at the beginning of this data set. Good. 1, 2, 4, 6, 8, 1, 2, 4, 8, 16, and the rest is nans. For the loop below, for lambda, we're going to take lambda underscore in the lambdas, but we're also creating this index, which starts from 0 using enumerate. That will be useful to allow us to stick the performance in the right row. Model, ridge, model, alpha, annoyingly, equals lambda, fit, intercept equals false, equals true actually, normalize equals false. Now, do you know why I set normalize equal to false and why I told you to set normalize equal to false? Well, if you do, tell me, because I don't. I can't think of why I would ever set normalize equal to false when doing ridge regression. We discussed this when features are measured on different scales, or even the same feature is measured on different scales. You can get different models unless you normalize first. So it totally beats me why I did that. If I remember at the end, we can redo this with normalize equals true. I wonder if we'll get a better model. Okay, we fitted the data, now we have to predict model.predict on xtrain, and we need also to predict on the validation, and now we need to use our loss functions, function MAE, good, those are our actual target variables, and we also need to compare it against what we're predicting, which is model predict train and model predict val. These errors come up, they're not very dreadful errors, they come up because of the way I've indexed into this particular data set here. There is almost certainly a better way. If you know it, please let me know. Post something on Moodle. Right. The lambdas we're seeing here at the tail end of the results, they're massive lambdas. At this value of lambda, at this massive value of lambda, we're probably going to be fitting an intercept-only model. So we should not be surprised to see these massive mean absolute errors. You might remember that the MAE within our simple linear regression was around about 27,000? Well, this is miles worse. Now, let's just run this code and have a look at what the graph here produces. Train invalidation. So on the x-axis we have models of increasing complexity. On the y-axis we have the log of the error, just so things show up a bit more clearly. No special reason to have the log there. And you see that for an insanely simple model, a very simple model, intercept only, probably, the performance is dreadful. But let's look at the train data first. As the complexity of the model increases, the train performance just gets better and better and better. But what happens to the validation error? Well, the validation error improves till about over here, where lambda is probably e to the 5 or something like that. But after that, it's actually getting slightly worse. So what is happening? The model is getting more complicated. It's picking up signal over here. It's picking up something real. The difference between these two curves, as it opens up, that suggests the model is beginning to pick up lots of noise and only a little bit of extra real signal. But by the time it gets to this level of complexity over here, anything else that the model is picking up is pure noise in the training data, and it's not helping validation performance at all. If we have a look at exactly the same kind of graph for the mean absolute error, it's a bit more clear in this one. You can see that the optimum point for mean absolute error is slightly different. This does illustrate something which we've never really spoken about, that when you're fitting models, you need to know what your performance metric is before you fit the model, because the best complexity for a given model can actually depend on how you measure success. I hope that made sense. It was a bit rushed. Please ask questions on Moodle if you're unclear about anything that I just said. Right, some questions. Do the models on the left suffer from bias or variance? You should know that. These models are astonishingly simple. They definitely don't suffer from variance. They're not picking up noise. They're not picking up anything. They suffer from bias because they're so simple they couldn't possibly pick up the real-life relationships. The models over here, we just talked about that, especially as that distance opens up over there. They are picking up huge amounts of variance. Does the model chosen by the optimal point on the validation curve suffer from bias or variance? Well, when I asked that question, I probably knew the answer. It certainly suffers from variance, because there's the only models which don't suffer from variance are where the train and validation error are quite close together. That opening up is a suggestion that you're beginning to suffer from variance, and by the time it gets pretty big, like it is over there, we're definitely suffering from some variance. But is this model suffering from bias? Is it unable to pick up the real life relationships? I don't know that you can tell from this particular graph whether the best model suffers from bias. Maybe I thought I did know at one stage. Now, moving on. Find the value of lambda which gives the best validation MAE. Well, the validation AEs are given in DF results. We want the best one. You could probably do this directly in pandas, but I sometimes prefer to be a little bit old-fashioned. So here are the validation errors. MAE val. We'll turn them into an array just so that pandas can deal with them. NP dot, just so that NumPy can deal with them natively. Argument tells us which one of those contains the minimum value. It's index number 8 which contains the minimum value, and so now we need to pick up the value at index number 8. The best lambda is 256. The model is just going to be exactly the same as we had before. I'm going to cheat, pick it up from here, although it probably would have been quicker just to type it. Now we use the best lambda, model.fit. We're going to fit now to the full train and validation data together. And once again, we have to predict loads of stuff, so let's predict it. How does the test error compare to non-regularized regression? Brilliantly. I think that previously we had something like 20,000 or even 27,000, now we're down to 15,000. I still think making a mistake of $15,000 in a house price isn't a very good idea, especially in those days when the house prices were a bit lower than they are today. Why are train and val errors similar? Well, because our model was trained on both of those. Why is test error so much higher than train error, or val error for that matter? Because there's a whole lot of variance in our model. Our model has overfitted itself to the noise in the train plus validation error, and this shows up in that big gap over there. That is it. I hope you followed this. If you did, you've fitted a penalized, you fitted a ridge regression in sklearn. That's a pretty good start. But we are going to move on. There's a lot more to do. We now need to go back and look at L1 penalization, and then a little bit more after that as well. Let's keep on going.